And the next thing that we need to think about, right? So we've considered flow throughout the boundary. What can also happen in general, depending on the vector field, is that the inside the rectangle might also produce flow or reduce flow. And there are two main ways that this can occur, physically speaking. Right, the flow inside. The next thing we got to consider, and we'll start. I'll circle this because this is going to be a big piece of what we use to get our final equation. We have flow through the boundary is approximated by this summation. And the next thing that we have to consider is flow inside the rectangle. So flow produced inside the rectangle. This is the next thing that we need to consider. And there are two main physical ways that this can happen. Right? The first main way that we'll consider is what's called rarefaction. And what this means is it's compression or an expansion. And a good way of thinking of what compression or rarefaction is if you think of what's called a compression wave, where there's regions of the gas compressing and expanding. Right. So this flow through the boundary should be directly balanced with any rarefaction that's going on inside of this region. So we can directly express that very, very nicely, actually, in the following way. So if we consider how to approximate the total change in mass due to rarefaction per unit time, you'll see that this is approximately equal to negative rate of change of density with respect to time evaluated at the point R multiplied by the volume of the region, delta X, delta Y, delta Z. So remember, all of these approximations only work when delta X, delta Y, and delta Z are small enough and the fields are smooth enough to do these types of approximations. But the idea is that this definitely has the correct units. The units of this are mass over time. And this gives us a nice approximation to the change in mass inside the region due to rarefaction. Rarefaction, so that's compression or expansion. And the main idea here is that if the rate of change of density is positive with respect to time inside this region, that means the change in mass is going to be negative. And if the rate of change of density inside the region is negative due to rarefaction or compression, then that means that you'll have a negative value here times a positive value, which means the change in mass due to rarefaction per unit time is going to be positive, because you get negative times negative, which is positive. So this is kind of a very nice justification of why this directly works. And then the other thing is that there are two things that we have to worry about inside the rectangular prism for the mass balance. The other thing that we have to worry about is what's called a distributed source of mass. So if there's something inside this region that's kind of like a pump or producing mass inside the region, that's what we mean by distributed source. And we'll denote this as a function. We'll say that Q of R comma T is exactly the function that gives us the production of mass at the point R and the time T. And this is measured in, it's per unit volume per unit time. And the change in mass, shouldn't be surprising that the change in mass due to this distributed source per unit time is approximately equal to this function Q at the point R multiplied by delta X, delta Y, delta Z. And this is for the exact same region, because this Q is a rate of mass production per unit volume per unit time. So if we have that the change in mass due to source per unit time, or sink per unit time for that matter, if Q is negative, is going to be just the value of this production of mass per unit volume per unit time multiplied by the volume delta X, delta Y, delta Z. And this is a valid approximation as long as the delta X, delta Y, and delta Z are small enough. So it's at this point now, right, where we kind of combine everything that we've done, and we're at the final step that we need. So we need to take the three approximations that we've just discussed. So that's rarefaction and distributed source of mass for flow of mass inside the rectangular prism, and also then connect these with the total net change in mass per unit time across the boundary. And this is done as follows. This is, in this example, used to express the conservation of mass. And it's also sometimes called a mass balance. And what we need when we're doing this mass balance is to say the following. We need to essentially express that the total flow of mass, or net flow of mass, into and out of this this region, this rectangle R, this rectangular prism, has to be directly equal to the total amount of rarefaction and mass production slash sinking inside the region itself. Right, so this is what gives us the so-called mass balance here. And sure enough, if we write this out, what this says is that the x partial derivative of density times velocity v1, or this is at that back face, y plus delta y over 2, plus the y partial derivative, other way around, it should be x plus delta x over 2, the y partial derivative of rho times v2 at the back face, y plus delta y over 2, plus the z partial derivative of rho times v3 at z plus z over 2, all of this times delta x, delta y, delta z. This should be exactly equal to, this gives us the net flow of mass through the boundary. This should be exactly equal to negative d rho dt, the partial derivative of density with respect to time, plus the source rate. All of this is evaluated at the point R, and this has been multiplied by delta x, delta y, delta z. And what we have is that, first off, the volume, delta x, delta y, delta z, ends up dividing out. So we have a nice simplification here. And not only that, but this should be delta, the delta right here, and a delta right here. What we're really considering, right, this is all an approximation until we take the limit as delta x, delta y, delta z go to 0. Because that's going to make, essentially give us what we're looking at, which is all of these expressions are approximations, right, and they become equalities when delta x, delta y, and delta z go to 0, or this cube shrinks down to the point, just the point itself R. And so as we do that, right, or as delta x, delta y, and delta z tend to 0, what we get is the following equation that has to be satisfied. and this is something that has to be satisfied at the point R. But you'll notice that there's nothing special about this point R, and specifically, if we go back to our plot of the vector field itself, so if we kind of go back and we open up that plot, we can do it for either of the two examples. This point R that we're kind of talking about could really be any point inside the vector field. Right, so it's this power that we essentially have, that this equation has to be valid at every single point in the vector field. And this is why this is so important, because what we've just done is essentially derive what's called the continuity equation. And this is an example of the three-dimensional continuity equation, or the three-dimensional equation that expresses conservation of a given quantity, conservation of the quantity rho, in this case, the mass density function. The continuity equation in 3D, it expresses conservation of the quantity rho. In our example, this is the mass density in 3D. Right, so through a three-dimensional domain. And this is a very, very, very important equation. But the reason that I chose to derive this equation specifically is because this gives us an exact way forward in motivation for deriving what's called the divergence of a vector field. Right, the left-hand side of the continuity equation. And I should reference that this is the continuity equation in Cartesian coordinates. So x, y, and z coordinates. Right, but the left-hand side of this equation I'll call this equation star, is actually a very special operation called the divergence of the vector field F, where the vector field F is the vector field with components rho v1, rho v2, or rho v3, which is the same thing as rho times v1, or rho times v. But just could as easily be, call it vector field PQR, where PQ and R are the function, these functions rho v1, rho v2, rho v3. So this is why I'm using the continuity equation to essentially motivate the divergence. So the divergence of a vector field F, a general vector field PQR, is defined as follows. We say that it's div of F. We'll use our underline notation. In Cartesian coordinates, the partial derivative of P with respect to X plus the partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. By the way, we can kind of write this in a clever way by remembering that with the dot product, we can think of this in some sense as a dot product of a special operator called the del operator with the vector F. Now, this is not a normal dot product, because this del is not an actual operator. Recall that the gradient of a scalar field phi is a row vector of partial derivatives, d phi dx, d phi dy, d phi dz. So we can consider the operator del is defined by x partial derivative in the first component, the y partial derivative in the second component, and the z partial derivative in the third component. We can also write this as 1, 0, 0 times the partial derivative with respect to x plus 0, 1, 0 times the partial derivative with respect to y plus 0, 0, 1 times the partial derivative with respect to z, which is the same thing as I hat transpose ddx plus j hat transpose ddy plus k hat transpose ddz. And this is sometimes the most convenient way of changing to a new coordinate system, changing bases, and something we have to be very careful about if we kind of try to view what the divergence looks like in a new coordinate system. So we'll get into that a little bit later. But what's nice about this expression right here, the divergence expression right here, is that the continuity equation, or the balance of mass, actually ends up looking like this. It's that the divergence of the vector field rho times v is equal to q minus partial rho partial t, d rho dt. And remember, the divergence of rho v is the same thing as this del dot product with rho v. This is one way of rewriting this continuity equation. An equivalent way of rewriting it is writing it as d rho dt. We add d rho dt to both sides. It's d rho dt plus the divergence of rho v, rho times v, is equal to q. And this is another common way of looking at and reading the continuity equation. This way is nice for a number of different reasons. One of the main reasons is that we can actually look at this in a slightly different manner, right? One of the properties of the divergence that's really nice, and I recommend you going through and showing, is that as long as the vector field v and the scalar field rho are smooth enough, the divergence obeys a sort of product rule. So I'm not going to go over all of the properties in detail, but one nice property that we have here is that the divergence of rho v, and proving this isn't too bad. This is as long as rho and v are smooth enough functions. That means is that enough of the derivatives are continuous. Then we have that the divergence of rho times v. Well, if you look at this component wise, this ends up being in Cartesian coordinates the x partial derivative of rho times v1 plus the y partial derivative of rho times v2 plus the z partial derivative of rho times v3. And each one of these combinations is a function times a function, so the normal product rule is obeyed. And I'm going to let you fill in the details here. It's a very good exercise. But what ends up happening is that this actually becomes the gradient of rho dot product with v plus rho times the divergence of v. And this is a sort of product rule that is obeyed by the divergence. And what's nice about this and kind of useful about this is that this can be rewritten to be here this is the rate of change of density with respect to time plus now this will be the gradient of rho dot product with v plus rho times the divergence of v is equal to q, is the same as this expression right here. And we can simplify this a little bit more, right? This expression right here for this quantity, the first two terms in this summation, is actually what's known as the material derivative. Because if you're following a point particle traveling along some path through this vector field, so you have some path line, some curve, right, which is a path line, where the velocity of the particle is along this field. Let's say the velocity of the particle, this curve is given by r of t, the velocity of the particle, then r prime of t, we'll say, is equal to v, the velocity vector field of this fluid flow, and you want to figure out what the total derivative of the density function is along this curve, or the total derivative ddt of the density function along r of t, and where density function is also a explicit function of time. By the multivariable chain rule, this is exactly equal to the partial derivative of rho with respect to t plus the sum of all the partial derivatives of rho with respect to x, y, and z times the velocity component in each one of those directions, which simplifies to this as we've shown before. This is why we sometimes call this entire thing the material derivative, and we just call it d rho dt, where it's normal to use lowercase d's for the derivative. The material derivative has a slightly different notation here across many math and engineering texts. So in fluid dynamics, this is then plus rho times the divergence of v, that's still equal to q. So this is an alternative way of writing down the continuity equation in terms of the material derivative, or in terms of how this expression changes along path lines of individual particles. So we can give a good kind of summary of exactly what it is the divergence of a given vector field means. And it's kind of an intuitive summary here. And what we'll do is we'll consider the divergence in 2D, not in 3D, but this interpretation also holds in 3D as well. This is the sort of physical interpretation. So the idea here is that the following, it's first off in 2D, this interpretation is in 2D, but like I said, it also applies in 3D. In 2D, the divergence of some vector field, we'll call it capital V, where we have V1 and V2, V1 and V2, V1 and V2. Divergence of the vector field V is the sum of the x partial derivative in Cartesian coordinates of V1 plus the the y partial derivative of V2. And at a given point, say R, if the x partial derivative at R is positive and the y partial derivative at R is positive, then that's going to mean the divergence is positive. And in general, we can kind of think of R as a source point. Right? In general, if you put a box around R, in this case in 2D, but this also holds in 3D, when the divergence is positive, that means in general there's more vectors flowing out of the point at R from this vector field than flowing in. And so R is, in some sense, it's kind of like a source. And to the direct contrary of that, right, if both of these partial derivatives are negative, then we can think of the point R as being a sort of sink, right? Because this is saying that R, in general, if you draw a small box around R, the point R, when the divergence is negative, there's more vectors going into the box than coming out of the box. So that's essentially what this is saying. And this even applies if these derivatives are mixed. So if, say, V1 is positive and V1 is negative, well, the sum of those two values is either going to be positive or negative, right, depending on which one's a bigger value or has a bigger magnitude. And this is still going to tell you exactly the same interpretation that I was giving before. If this is positive, if the divergence is positive, then R is kind of like a source of vectors, because there's more vectors going away from R than going into the box around R. If the divergence is negative, then there's more vectors going into the box than coming out of the box. And then the last case, if the divergence is equal to 0 at a point, then that means the total amount of vectors going into any small box around the point is exactly equal to the total amount of vectors going out of any box around that point. So there's no source or sink. The point is neither a source nor a sink. And this is actually, it brings us to a very interesting, definition of what's called an incompressible vector field. So we define an incompressible and this is typically reserved for fluid flow fields, but it could apply to any vector field. Vector field is sometimes called a solenoidal vector field as well as a vector field or else just say if the divergence is equal to 0. Within some region. Omega. And really we'll be very, very clear here. This is only within the region omega that it's said to be solenoidal or incompressible. So we say that the vector field F is solenoidal or incompressible within some region omega if the divergence of the vector field is equal to 0. Within the region omega. And I'll be specific here, we'll say the divergence of F, of the vector field F. Because and this makes a lot of sense in some ways, in a lot of ways. So we'll include solenoidal as the main definition here, but incompressible is also a good way of thinking of this. So the idea here is that the vector field F is solenoidal within omega if the divergence of F is equal to 0 within some region omega. This is incompressible is a nice word here because the idea is that when the divergence is equal to 0, that at any point, that means that that point is neither a source nor a sink. So what that's telling you is the following: it's if you have some region in three-dimensional space, call this region omega here. This is a 3D region in general. If the divergence is equal to 0 of a vector field at every single point inside this region, that's like saying there's no sources or sinks at any single point inside this region, right? Which is why we can say that this is the same thing as incompressibility in some sense, and this is directly related to the idea of incompressibility in fluid dynamics, right? When we talk about incompressible fluids. By the way, if a fluid velocity field is incompressible, then the continuity equation does simplify a little bit as long as the solution is valid and the functions are smooth enough. It simplifies to just the material derivative is equal to the source function, because this divergence is equal to 0 for incompressible fluids. So this gives us this definition right here. And this should wrap up our understanding of the divergence of a vector field.